All right, for this example, we've got a gear that's attached to a smaller gear that's being rotated, looks like by a motor that's going 4.5 radians per second squared. It's going clockwise, which would make this rotate counterclockwise. And then it's got this drum that's attached to that gear. So it's also going to rotate the same as this gear B. And then it's going to be pulling in this cord, which will lift up block C. So we've got an idea of what's going on here. It's starting from rest, and we want to find the velocity of that cylinder after 3 seconds and the distance it travels. Okay, so if this is a constant angular acceleration, that's going to help us out. But we're going to have to be able to go from this 75 millimeter gear A to this 225 millimeter gear B with their respective radii, and then go to this drum D or pulley, whatever they call it, and then to the velocity of C somehow. So we need to start thinking about how those are related. And basically, if we think about the interface between those, right? The each point going around this circle has to be going the same speed as each point going around circle A, right? Because they mesh together here at point P. So if you imagine those going together, the outside of both of those circles, even though they're different sizes, they need to be going the same speed, right? Which means if this goes around one time, this circle will go around a fraction of a time, right? So it's going to be spinning a lot to make this go around one time. So that's how those are related, is basically their position, their linear position, linear velocity, linear acceleration is the same at point P, right? At their interface there. Now, between B and D, this pulley, do they have the same linear anything? No, right? If you look at the outside point of this gear, it's going to have a different S, V, and A than the outside of pulley D here at P prime, for example, right? And that's going to be the speed at which it pulls the cord in. So we can't equate those using the linear ones, but what is the same about B and D? They've got the same spinning everything, right? They don't have the same linear anything, but they have the same angular radians, right? Theta, omega, and alpha for our angular position, velocity, and acceleration. So that's how these two are going to be related. So we can relate these A and B using the fact that they have the same linear at the interface, position, velocity, acceleration, and B to D, we can relate using the fact that they have the same angular everything, position, velocity, acceleration. So that's where we're going to go with it. So let's try it out. We've got gear A and B. They've got the same tangential speed at the point where they mesh, like we were saying. So we can say they have the same tangential acceleration at that point P there, right? So for the gear A, that tangential acceleration is equal to alpha times r, right? Our equations for relating the linear to the um, angular, right? So if we take the radius of A, which is the 75 millimeters, and multiply that by the 4.5 radians per second, that would give us this tangential acceleration of some particle going around, which would be the same as the tangential acceleration of some particle going around the outside of block gear B. So that's what we're saying here. Alpha R for gear A is the same as alpha R for gear B because they both have the equal linear tangential acceleration. Right? So we plug in our known acceleration there, plug in our 75 millimeter radius. We're looking for alpha B, plug in the 225 millimeter radius for it, and we turn the crank out, pops alpha B 1.5 radians per second squared, which It's basically just a ratio, right? That's all these equations are going to be giving us is a ratio, a gear ratio between the the 75 millimeter and the 25 millimeter, right? It's 75 divided by 25, 225 is our ratio between B to A. All right, now since B is attached to D, like we were saying, or D is attached to B rather, then we know they have the same angular accelerations. So now alpha D equals that 1.5. You see where we're going with this? We need its tangential velocity. So let's get its tangential acceleration maybe, and then we could use some constant accelerations. So if we get its tangential acceleration by doing that alpha times the radius, right, of 0.125 is this 125 millimeters, then we'll get its upward acceleration, its tangential acceleration of some particle going around the pulley D is 0.1875 meters per second squared. So that's pretty nice. This is wrapping itself around that at 0.1875 meters per second squared. Now we've got a constant acceleration for some particle coming up on this rope, which could help us to find the velocity and the distance in 3 seconds. So that's the last part. The velocity after 3 seconds would just be constant acceleration, 0.1875, starting from rest, so 0. And 3 seconds, we get a velocity after 3 seconds for the cylinder of 0.563 meters per second going up. And use your constant acceleration for finding the position as well for C, which is the cylinder. Starts from the bottom, 0, starts from rest, 0 velocity, 1/2 a t of 3 seconds squared. And that's what we get for the position that it has moved in those 3 seconds. Okay, so pretty nice. We can combine a little bit of what we knew before with these new ideas where we've got the radius giving us a relationship between different gear elements and whatnot. So that's a pretty good example of what we'll want to do and what we're able to do now that we have these uh, fixed axis rotation relationships.